I'm done with school.
Are you a senior?
What?
Are you a senior?
Yeah, I'm out of here. I'm done.
You got like 6 weeks still.
Okay, but like, I'm done.
26 days of school left.
Woo! Yay! Oh my gosh, what's the
It's like really going. It's like no time.
Okay.
And my shoulder's broken.
I know.
How'd that happen?
I have to
But how'd it happen?
volleyball.
You fell on it? Too many spikes?
Yeah, I was just too good. Just had to like humble me for a minute.
No.
Bring me down to earth.
Are you playing college volleyball?
No, I hate volleyball.
Oh, okay. Well, that's
Dang.
I
okay.
got my awards, now I'm done.
That's honest.
Good for college, huh?
I know.
All right, folks. Well, today we're going to start chapter 14.
I have a question.
Yeah, hi.
How many chapters are we going to have? At least for the seniors.
1 or 2?
Okay, that's not bad. So really feels good.
No, it's okay.
Allie, are you ready? Wow.
So, chapter 14 is all about rational functions. Again, this should have been something that you talked about in your Algebra 2 class. Maybe it'll ring a bell, maybe it won't, but possibly have done it before. We say a rational function is something of the form f of x equals p of x over q of x, where p and q are polynomials. Boy, my computer is just like limping along here. I don't know why it's being so slow. May have a restart in its future here. Okay. So, first things first, we talk about a new type of function. Let's talk about how we find its domain. Oops. Okay. So remember when we talked about finding domains in first semester? So let's look at our function here. What operations do we see going on in this function? Division, addition, subtraction. I see multiplication too, between the 2 and the x. Of those, which is the one that we really care about? The division, right? Because I know if I divide by what gets me in trouble? Dividing by 0. So to find the domain for this rational function, I'm just going to worry about where the denominator can be equal to 0. Right? So I know that, let's make that not equal, I guess. I know that that's the only x value that is going to cause this function to become undefined. So we say the domain then is the set of x's that are between negative infinity and 1/2, or between 1/2 and positive infinity. Feel okay doing that? Ring a bell? Thought we tried to do a pretty good job of that on first semester, knowing that we're going to circle back to some of these ideas later on. Let's do another just to make sure. All right. Once again, finding the domain, the only thing we care about is, the denominator equaling 0. Now, how am I going to solve x cubed minus 4x? Okay, start by factoring out an x. Great idea. Okay, then what? And I wouldn't do a square root yet. Well, look at the x squared minus 4. Does that look like something? Yes, that's a difference of 2 squares, so that can factor to x plus 2, x minus 2. And now that I have it completely factored, I can set each piece not equal to 0. So those are the 3 values that x cannot take. Any other x's, though, would be fine. So my x's could go from negative infinity to what value? I can't do a plus or minus with an interval. I would not do 0 here. Has to be the smallest one first, right? And then negative 2 to what number? Not positive 2. 0, the next smallest number. And then 0 to 2. And then 2 to positive infinity. Always smallest to biggest, yes. Right? If I did between like negative infinity and 0, well, negative 2 is in there, and I can't have negative 2, right? So we have to, as we build our intervals, we have to go from smallest exception to biggest exception, always. We feel okay doing that? Shouldn't have been too bad. Ava, if you would have, at this point, separated, you could have gone this route. Oops. And square rooted both sides and done it that way also. I would not recommend doing that, but it would have been okay. You said use a square root, and I assume this is kind of what you meant. And that is okay. It just, I think that leaves some room for bad stuff to happen. Okay. So the topic we're going to start with is graphing. So when we're graphing, there's several key features that we're going to want to include in our graph. The first key feature are the discontinuities. And there's 2 types. So the first is a vertical asymptote. To find the vertical asymptotes, we set the reduced denominator equal to 0 and solve. The other type of discontinuity we can have is called a removable discontinuity. Say we're going to set each factor reduced completely from the denominator equal to 0 and solve. All right. Let's do a quickie example here. About just finding these discontinuities. We'll talk about how to graph them in a little bit. But let's just talk about finding them algebraically first. Okay, so let's say we have y equals x squared plus 5x plus 6 over x squared minus 9. So to do this, the first thing I want to do is to see if I can reduce this rational function at all. To reduce a rational function, what must we do first? Has to be factored. Who can tell me how to factor x squared plus 5x plus 6? It's not x plus 5 and x plus 1. It needs to multiply to give you 6 and add to give you 3. Good. So x plus 2 and x plus 3. So then x minus 3 and x plus 3. What do we notice? The x plus 3's can cancel. So for my vertical asymptotes, I'm going to take the reduced denominator, set equal to 0 and solve. For my removable discontinuity, I'm going to take the factor completely eliminated from the denominator. That's the x plus 3. I'll set that equal to 0 and solve. So that's my x. A removable discontinuity, though, is a point. Like it's an open circle on the graph. So I also need a y-coordinate for it. To get the y-coordinate, I'm going to plug that x that I just found back into my reduced function. So I'm plugging it back into there, which gives me negative 1 over negative 6, or just 1/6. That's my removable. Does every function have both of these? No. Does it have to have either of them? No. Are you going to see a lot of removable discontinuities? Probably not. Not in practice. Doesn't happen very often. But it could. I want to do one more example, and then we're going to continue on. Okie dokes. Okay, so let's say we have x squared plus 4x plus 3 over x squared plus 6x plus 9. First step is to factor. How does the top factor? Again, multiplies, adds. Good. And the denominator? 3 and 3. Okay. Can reduce. So, what do I use for my vertical asymptote? X plus 3 equal to 0. So I get negative 3 for that. How about my removable? No. Read it again. Completely. Are all of the x plus 3's gone from my denominator? No. Even though I crossed one out, there's still one left. So there's going to be no removable discontinuity here. Okay? So when we say reduced completely, it means all of that kind of factor are gone. So since I still had an x plus 3 left, it is not removed. That's why the name is there. It's still there, so it doesn't count. You guys feel good about that? That's usually the trickiest situation, is when that happens. Okay? If I had like x squared plus 1 as the denominator, where the solutions to that are imaginary, does that feel okay? All right. The next thing we're going to have are our end behavior asymptotes. And here we can have 3 cases. We can have y equals 0. This occurs if the degree of the numerator is less than the degree for the denominator. So if I have the function y equals x over x squared plus 1, the degree in the numerator is 1, right? Because it's x to the first. The degree in the denominator is 2, because the biggest one is x squared. Since the degree of the numerator is less than the degree of the denominator, my end behavior asymptote is y equals 0. That's it. That's all I'm looking at. Feel good? The next situation, we could have the asymptote y equals a sub n over b sub n, where a sub n is the leading coefficient of the numerator and b sub n is the leading coefficient of the denominator. We do that if the degree of the numerator and denominator are equal. So for example, if I have y equals 2x plus 5 over x minus 1. Well, what's the degree of the numerator? 1. What's the degree of the denominator? 1. They're equal, so I'm going to have then and end behavior asymptote of y equals the leading coefficient of the numerator over the leading coefficient of the denominator, y equals 2. Does that feel okay there? The third situation is where y equals q of x, some function of x. So that q of x is the quotient of the division problem numerator divided by denominator. And we do that if the degree of the numerator is greater than the degree of the denominator. So for example, say we have let's say we have y equals x squared minus 2x plus 1 over x plus 2. The degree of the numerator is 2. The degree of the denominator is 1. So that fits that third criteria. So I need to do polynomial division. I need to do x squared minus 2x plus 1 divided by x plus 2. How should I do that polynomial division? Long division or synthetic division? Synthetic division. I can do that because the divisor has degree 1 and leading coefficient of 1, right? You guys thought you were going to be done with that polynomial division, right? So what's the quotient of this division problem? X minus 4. Do I care what the remainder is? I do not. It doesn't matter for this. So my end behavior asymptote is y equals x minus 4. Cool? Will you have to do polynomial long division at times? Maybe. Maybe. Hopefully not, though, right? Hopefully Mr. Kulik's giving you something you can just do synthetic division and get out of there quickly and easily, but doesn't have to. Okay, those are the three situations for finding these asymptote end behaviors. The third thing we need are the zeros. To find those, we're just going to set the reduced, should include that, numerator equal to 0 and then solve. So note that this is the reduced numerator. So first step I want to do is factor to see if I can do any reducing. How do I factor that numerator? Yeah, x minus 6, x plus 1. Good. And the denominator? Okay. So I can reduce. So now all I need to do is take my reduced numerator, set that equal to 0, and solve. So that means that I have the 0, 6, comma 0. Everybody feel good? Notice that x plus 1 doesn't count because I reduced it. That'll actually be a removable discontinuity. Everybody's okay there? Okay.
Why did you cross out the tag?
Because they were the x plus 1s. I just wrote it the order he said it. So I just, Cool? Okay. And then the last thing we'll want are y-intercepts. How do we find those?
Plug back.
Just plug 0 in for x and evaluate, right? Sound good? All right, let's do some examples of actually constructing some graphs out of this with this information. Cool? So everything we do requires a reduced fraction, right? So right from the jump, I'm going to just factor this to see if I have anything to reduce. Do you see anything to reduce? Nope. Will that happen a lot? Yup. All right. So discontinuities. I can only have vertical asymptotes since I didn't reduce anything. Everybody agree? So to find those, I'm just going to take each factor from the denominator, set it equal to 0, and solve. Cool there. Next thing I'm going to do is find my end behavior asymptote. What's the degree of the numerator? Is 1, and the degree denominator is 2. So that's the degree of the numerator is less than the degree of the denominator. What happens there? That's y equals 0. So far, so good? Okay, I'm going to calculate my zeros. To do that, I'm just going to take my numerator and set it equal to 0. Cool. And the last thing I'm going to get is my y-intercept.
For the zeros, you'd be taking the numerator of the factor.
Of the, yes. Yeah, I would use the factored numerator. Everybody, so far so good. Now what I want to do is take this information and build a graph out of this. Cool? All right. So I'd like to draw on my asymptotes first. So far, so good. Okay, I have 1, 0, and then like 0, 1/4. And now I need to draw the rest of my graph. So I know that y equals 0, the graph is either going to be doing like, and those vertical asymptotes there, I know it's going to either doing this or this, right?
How do you know it's doing it?
Because it's not supposed to cross the asymptotes. So it's either going to be up, like up above y equals 0 and before x equals -2, or it's going to be below y equals 0 and before x equals -2. So what I'm going to do is I'm just going to kind of pick a test value and kind of see what happens. So something less than -2 would be like -3. So that's going to give me a negative on top, but a positive on bottom, right? So that means that I'd have a negative number, so it should be down here. Is that okay?
Because you have a negative on top of positive.
Negative over positive is a negative number for y, so it should be below the y-axis. Does that feel okay?
Yeah.
All right. For this one, I know I'm either going to be like doing one of these or doing one of those to there. How am I going to figure it out? I'm going to pick a point in between and see if it's positive or negative. So should I be above or below? So I'm going to pick -1. So if I plug -1 into the numerator, I get a negative. If I plug -1 into the denominator, I get a negative. Negative over negative is positive. So I should have that piece. Now I need to see if I'm going to do this or if I'm going to do that. Sound good? So, again, I'll pick a test point. This is a little harder because I have 1 and then 2, so I have to do like 1.5, which is kind of stinky, but I'm not actually going to do the calculation. I'm just going to kind of see whether it's negative or positive. So if I plug 1.5 into the top, I have positive, but I plug 1.5 into the bottom, it's going to be negative, right? Because I know 2 squared is 4, and 1.5 is less than 2, so that'll be less than 4, right? So I have positive over negative, so I should have that one. And then my last part of my graph should either look like this or like this. How am I going to check? I'm going to do another test value. Let's do +3. Gives me a positive in the numerator and a positive in the denominator. Yep. Always, because the x-coordinate on the y-axis is 0. Right? Every point on the y-axis has x-coordinate 0. So it's always 0 for y-intercept. Yep. So there's a perfectly reasonable graph. Is everybody okay with kind of how I did that?
What if there is the end being here? What if that's not 0? Like, what if you have the denominator is small?
I got 2 more examples coming to cover all the different cases. So we'll see in just a second. Sound good? Beautiful. In general, I think these are usually the easiest ones when the numerator is smaller than the denominator. At least in my opinion. Okay. Typically, I'd start by factoring, but nothing to do there because they're all linear pieces, right? Okay. So we'll start with our discontinuities. Again, nothing to factor, so I know there can't be any removables, so we'll just go straight to our vertical asymptotes. Cool. And then we'll look at our end behavior asymptotes. So the degree of the numerator is the same as the degree of the denominator because they're both degree 1s. So there it's going to be the leading coefficient of the numerator, which is, nope, -1. And the leading coefficient of the denominator is 1. So we just really have y equals -1. Cool. Okay. Then we need our zeros. So we'll take our reduced numerator, set it equal to 0 when we get 2. Feel good? And then our y-intercept, we're just going to plug 0 in for x. So we have 0, 2/3. Sound good to you guys? This one will probably be easier than the last one because we only have one asymptote, or one vertical asymptote, so we don't have as many test sections. We might not have to do any tests, to be honest with you. Let's just see. So let's see, 1, 2. Test values. Then we have a 0 at 2, 0, and then 0, 2/3. Oops, it should be like there. Well, I know that this piece has got to do that, right? Does that feel okay, Luca?
Why you just go?
Well, I can't start from down here because I'd be crossing the asymptote to get to there. So the only way for me to get to these to connect those 2 points from the asymptote is from starting up top and then going down. That's the only way I can do that. Over here, though, we'll have to check to see which one I have. So I'll just pick -4.
You're picking a point on the further away.
I'm picking something over here, right? I just want to see, like, is that going to now be bigger than -1 or smaller than -1? So here I actually have to kind of...
It's got to be to the left, or it's got to be smaller than the
asymptote. Yeah, I'm usually picking, like in between the asymptotes. Here there's only one, so I have one side of the asymptote I covered. I didn't have to do anything there. The other side I'm just going to check now.
So you could do like -5.
Yes. Yes, absolutely.
Degrees the same as divide.
Leading coefficient over leading coefficient. Yeah. All right, so if I plug -4 and I get 6 over -1, so that's -6, right? So it should be that one, because that's way below y equals -1. And I'm good. I mean, you could think about it as like, okay, then I have like this point down here that's got to go through, but like, whatever. Good enough?
Can you go back to the first one and explain like where you're picking your point from, like on like where the points are?
Yeah, so I picked like what did I do? I picked like -3.
Yeah, that's the one that we just did.
Yeah, that's what you wanted, right?
For the other one, like the other points stuff. Like on the other side, yeah.
Okay, so you want this?
Yeah.
Okay.
Like what numbers?
So I picked what I tried to decide was like, is it going to do this or is it going to do this? And I guess I probably could have not really done this because I'm crossing here.
Oh,
I shouldn't have even checked. I knew it was the first option. And I know I have to go to here. And then I don't know if I'm going to do this or that. And that I would have to check.
because it's not a line. So
Yes, because so I don't know if it's just going to bounce off of it or if it's going to go through it. So that I have to check. So I just did like 1.5
Okay.
and got a negative value, so I know it had to go down.
Okay.
Something that was less than y equals 0.
So you want to pick between where the line would be and the point for that one?
I want to pick between where I'm at and the vertical asymptote.
Okay.
Right? Like I know up to this point,
Okay.
you know what I mean?
So one a little bigger.
Yeah. Does that feel okay?
Yeah.
All right.
Is it basically on the left side of the graph, you would choose one that's technically smaller than it's negative, and on the right side, you're choosing one that's bigger?
Yeah. I'm just like, so like when I look at this, I want to choose something from here,
Yeah.
like there, and then there. So I'm just like choosing it in between the x's.
Yeah.
Does that?
Yeah.
Okay. All right. I got one more example to do, and I think this should be where we stop today because this is not not trivial for us. And these problems are rather time consuming, so I don't want to do like a whole bunch of this and have you guys like, oh my God, I just got like 60 problems and they're like all an hour to do or something.
Is this all 14?
This is all just 14.1. 14.1 is just about graphing.
Wait, are we just doing that today, 14.1?
That's my plan.
Okay, perfect.
I'm glad you approve.
Yes, yes.
All right. Nothing to factor, right? Well, I guess I could factor the numerator. Let's do that. So if you have 4 terms like this, we want to try to use grouping. So key to grouping, though, is you have to have an addition sign in between your 2 groups. So I'm going to think about that minus x in the middle as plus a negative x. From the first group, I'm going to take out an x squared. From the second group, I'll take out a negative 1. Now, if I think about this as one thing and that as one thing, I notice I have an x plus 3 in common between them, right? So if I factor this out, the stuff that's left would be x squared minus 1. And x squared minus 1, hey, I've seen you before. That's just x plus 1, x minus 1. Everybody feel good there? All right. So my discontinuities, again, there's no reducing, so all I can have is vertical asymptotes. Set the denominator equal to 0. Well, there's nothing to do there. It's just done. My end behavior asymptotes. Oops. I notice the degree of the numerator is greater than the degree of the denominator. 3 to 1. Hold on one second. This isn't the problem I wanted to do. Crap. I just picked the wrong problem. Just take a chill pill, you goofs. My goodness gracious, we're just like... Sorry, I made a mistake. That's better. All right. So, again, start by trying to factor. Easy enough. I'll do my discontinuities. I can only have, stop talking please, vertical asymptote. So I set the denominator equal to 0, da-da-da. My end behavior asymptote, again, I know its degree of the numerator is greater than the degree of the denominator, because it's 2 is greater than 1. So I need to do that polynomial division. Since my divisor has leading coefficient of 1 and degree 1, I can do synthetic division. This is all I need. So y equals x minus 6.
I thought you just take the
That's if the degrees are equal. If the numerator is greater than the denominator, I do polynomial division, take the quotient. My zeros, I'm going to take my numerator set equal to 0. So I have 5 and -1 as solutions. So that's the 0.50 and the -10. And then my y-intercept, I set x equal to 0. So I get 0, -5/2. Is this okay? So far, so good? Okay. So let's start drawing our graph. Again, we like to start by drawing our asymptotes. So I have x equals -2. How do I graph x equals or y equals x minus 6? Well, I have to draw the equation for the line, right? To graph a line, how many points do I need? 2. So maybe I'll pick x to be, I don't know, like +2. If x is +2, what's y? -4. So 1, 2, 3, okay. Okay. And then maybe I'll pick 4. If x is 4, y is -2, right? So I had to extend my graph there quite a ways to get the intersection of those asymptotes in there. Okay. Is everybody okay with what I've drawn so far? You put my zeros in. So I have -1, 0. And then I have 5, 0. 1, 2. Okay. And then 0, -2.5. So right away, I can tell that like It's got to do one of those, right? Because I can't cross the asymptotes, and the only way to connect those 3 points is by doing that. So the other part of my graph is either going to look like this, or it's going to look like that. Everybody okay there? Now, this one, it's a little bit harder to tell what point to pick, right? What x value to test, because I have to then be below that line, y equals x minus 6. So here's what I'm going to do instead. Here's how I'm going to pick it. Hi, come on in. You're good. You're welcome. Mary. Don't look so excited.
Well.
So what I'm going to do is I'm going to pick something very close to -2. Because that should either be a really big number or a really small number, and it'll be really obvious what's going on. So let's say I pick -2.1. So that'll give me a negative down here, a negative up there, and then a negative right there. Agreed? So it's a negative number. So that tells me it's gotta be, and it's gonna be a pretty small negative, or like a very, very negative number, because I'm dividing by 0.1. So it's like multiplying by 10. Yeah, so it's very negative, right? So it's gonna be, it'll be this part right here. Because the other option would have been like, oh, then if it should be something way up here, right? It should be very positive. So it should be easy to tell the difference between whether it should be below the y equals x minus 6 or above y equals x minus 6. You could also pick the test value, actually find the number, and also then plug the same test value into y equals -6 and just check if it's above or below. You can do it that way also. Either is okay. You just want to do kind of like a checker to see where it needs to go. That feels good to me for today. Yes. So you guys should be able to do... Yeah, go ahead.
Is there technically a line on the other side?
A line on the other side. No. So there's not going to be anything here because it would fail a vertical line test. Right? Which I know that if this is a function, it can't do that. So I can't, again, if you draw it and you're not sure, like, do a little vertical line test. Can you draw something that's going to intersect the thing twice? Because that's very bad. You know you've made some kind of critical mistake there. So what I'd like for you guys to do is 1 through 8. And then I'd like you to do the 13 to 23. But I'd just do those as odds. But I wanted you to show how you got the 4 parts that you're going to graph, right? The discontinuity, the asymptote end behavior, the zeros, the y-intercept, just like we did before. I want to see that work in addition to your graph. Don't give me just a graph. Okay? And I'm stopping now because this feels like enough.
Happy weekend, everybody.